Welcome back to the deep dive. Today we're taking a bit of a strategic detour. We're not looking at flagship sedans or heavy trucks. We are stepping into, I think, the world's fastest growing but also most cost-constrained mobility sector, the micro low-speed electric vehicle, or, the micro LSEV.
And these really are not toys. That's the first thing to get your head around. They're critical solutions for urban mobility. Think of the Willing Mini EV that's just everywhere in Chinese cities, or the
hmm
Citroen Ami in Europe, which is so pragmatic. They're literally defining how people move in cities. But that lightness, that low cost, it poses these enormous, really unique safety challenges that, frankly, traditional automotive standards don't always address properly.
And that is exactly our mission today. We're putting on the hat of a chief systems engineer at, let's say, a top global automotive consultancy. And the task is huge. We have to synthesize global regulations, competitive benchmarks, component limits, all of it into one single comprehensive engineering requirement specification, the SOR for functional safety. This SR is the blueprint. It's what lets an engineering team build a micro LSEV from scratch that's affordable, mass-producible, and this is the key zero compromise safe.
And this really demands that McKinsey-style professional thinking because you're immediately hit with a fundamental strategic challenge of this market.
Yeah.
We have to define it right in the preamble of our SOR. We call it the dual constraint.
Ah, okay. The dual constraint. This is the tension at the heart of LSEV design, where the budget just slams right into the regulatory demands. How do we articulate that?
It's a tightrope walk. There's no other way to put it. On one side, reality one, extreme cost control pressure. I mean, to hit the price point for a fleet operator or just the mass market, you have to be looking at industrial-grade components, low-cost automotive chips. You just don't have the margin for the $50 or $100 safety microcontrollers you'd find in a high-end car.
Okay, so that's one side of vice.
The other side is reality two, exponentially increasing safety requirements. Global regulations are moving towards zero tolerance, especially for battery thermal runaway and control system failures. You need ASIL-D levels of safety, but you have an ASIL-A budget to work with.
So we're basically trying to deliver the safety performance of a premium EV, but with the bill of materials of a city scooter. If we can't afford that big, expensive hardware redundancy, what's the core strategy our SOR has to define?
It has to be two strategies working at the same time. First is risk-based tailoring of ISO 26262. This means we have to rigorously, and I mean rigorously, customize the ASILs based on the actual low-speed risk profile of the LSEV. You save money where it's safe to do so.
Okay, and the second?
Architectural decomposition. Instead of one big, expensive, super redundant chip doing everything, you split the safety functions across simpler, independent, and therefore cheaper monitoring layers and components. The SOR has to mandate this systematic approach, breaking down a big ASIL-D goal into smaller, manageable, lower ASIL requirements spread across the system.
All right, let's unpack that. I mean, we can't write a single line of code until we understand the rules of the road, so to speak. We have to start with the law, because the law dictates the engineering. Okay, so when you're starting any global vehicle program, the first thing on the list has to be the target market classification. It changes everything.
It changes everything, from crash testing to your ASIL targets. And for LSEVs, it's not just about compliance. You're strategically using advanced electronics to compensate for the fact that you have a lightweight, low-mass structure. You don't have 2 tons of steel to protect you.
Let's start with Europe then. It's so prescriptive with its L-class vehicles under that big regulation, EU 168/2013. That really defines the box we have to play in.
That's exactly right. Our SOR needs to understand the L6E and L7E classifications inside and out. So L6E, the light quadricycle, that's the Citroen Ami's world, is really restricted. Mass has to be under 425 kilograms, and that's excluding the battery.
Wow, that's light.
It is. Speed is capped at 45 kilometers an hour, and power can't go over 6 kilowatts. So those limits themselves are a form of passive safety.
And the L7E, that's more like the micro sedan our SRR is targeting.
The L7E, the heavy quadricycle, it pushes that envelope. It gives you a much more useful urban vehicle. The mass goes up a little to 450 kilos, again, without the battery, but critically, the power goes up to 15 kilowatts.
And that's what gets you up to that 80-kilometer-per-hour target.
Exactly. And that speed increase immediately raises the stakes for functional safety. Braking, unintended acceleration. It all becomes much more critical.
So what's the direct link to our functional safety paperwork? Where does the regulation point us?
Well, there's another EU regulation, 32114, that directly references ISO 2626212. That's the part of the standard specifically for motorcycles and light vehicles. So our SOR must reference it. It mandates that all your electronic controls, especially if you're using modern things like X-by-wire braking, have to prove they remain safe even when you inject faults.
Can you give an example?
Sure, if you have brake-by-wire, you have to prove that if a sensor fails or the CAN bus gets interrupted, you don't lose all braking. There has to be a fallback, a verifiable fault tolerance.
Okay, so Europe is all about verifiable fault tolerance. Let's pivot to China. It's the biggest opportunity, but also sounds like the biggest regulatory headache. The Wuling Mini EV is the leader there, but it doesn't always follow those simple quadricycle rules, does it?
No, and this is the first huge strategic fork in the road we have to account for. Most of those successful microsedans in China, like the Wuling, are classified as M1 passenger vehicles.
Not quadricycles.
Not quadricycles. This is a critical detail for our SOR. It means the manufacturer is choosing to meet, or is being forced to meet, the full passenger car crash and safety standards, the GB standards. So if your target includes China, you're immediately setting a much higher bar for passive safety, which then puts more demand on your active electronic systems.
Right. I get the strategy there. If you aim for the M1 classification for China, you're sort of future-proofing yourself for other markets. But you mentioned one specific regulation that's a real choke point for the entire battery architecture. Tell us about GB 38031-2025.
This is where China is setting the global benchmark. It's totally non-negotiable for any competitive EV. GB 38031-2025 is, I think, one of the world's most stringent battery standards, and it just fundamentally changes how you define failure. Historically, a lot of standards were okay with a 5-minute warning. You get a signal that thermal runaway is starting, and you got 5 minutes for people to get out before the fire.
And GB 38031-2025 gets rid of that warning.
It replaces it completely. The mandate is for total containment. The standard says that after thermal runaway is triggered in one cell, the battery pack must achieve no fire, no explosion.
Wow.
Yeah. You're not relying on escape time anymore. You're relying on engineered containment. And for a low-cost LSEV, that's a monumental requirement. It forces you to spend money on robust materials, inner cell barriers, venting systems, all costs that fight against that dual constraint we talked about.
So it seems like Europe is focused on electronic fault tolerance in real time, while China forces you to contain a catastrophic chemical failure. We have to design for both. What about Japan and the US, just to complete the picture?
Japan, with its ultra-compact mobility class, think Toyota C+ pod, they just have a culture of high engineering standards. These vehicles tend to follow strict internal quality rules that align with ISO anyway. The U.S. has its FMVSS 500 LSV category. Historically, it's been a bit looser on passive, safetyless need for advanced crash structures, but battery safety, driven by standards like UL 2580, is catching up fast. The global trend, really pushed by that GB standard, is zero tolerance for thermal events, no matter how small the car is.
Okay, so the anchor point for our SRR is clear. We have to target L70 performance to get that 80 km/h speed, and we have to be able to pass the GB 38031-2025 test. That means our battery is A sealed E, and our torque path has to be a high A style as well.
Correct, and that anchor point immediately forces our hand. We have to address the most critical hardware decision that will dictate, I'd say, 60% of our safety requirements.
And that is?
The core electrical architecture.
All right, let's set the baseline for our SR project, just so everyone's on the same page. We're designing an L7 micro sedan, top speed, 80 kilometers an hour, a competitive range of 150 kilometers, and we're using an LFP battery.
And this first, most foundational decision for the team is the system voltage. It's a binary choice. Do we go with strategic path A, 48 volts, or strategic path B, high voltage? That choice completely reframes the entire safety problem.
Okay, let's walk through strategic path A, the 48V safety voltage. This is the route the Citroën Ami took. Why is 48V so attractive when you're under such cost pressure?
The appeal is massive. It's a huge reduction in cost and regulatory complexity. And it all comes down to one magic number, 60 volts DC. If your system voltage stays strictly below 60 VC, it legally qualifies as safety extra low voltage, or SLV.
And for a cost-conscious LSEV team, that's like finding gold.
It is, because you legally sidestep entire categories of complex, expensive high-voltage systems.
Like what, specifically? What do we get to avoid?
You eliminate the need for a high-voltage interlock loop, or HVIL. You don't need an insulation monitoring device, or IMD. No specialized shielding. No expensive high-voltage contactors. None of that expensive IPX XTP protection on all your connectors. Even the service technicians don't need the same level of high-voltage safety training. The component count, the complexity, it just plummets.
That sounds like millions in development and certification, plus maybe hundreds of dollars per car. Strategically, why would anyone ever choose Path B if Path A saves so much?
Because Path A hits a performance ceiling. To get to that 80-kilometer target, to manage the torque and get 150 kilometers of range, you need power, probably 12 to 15 kilowatts. In a 48V system, just to get 6 kilowatts, you're already pulling around 125 amps. To get to 15 kilowatts, now you're talking about continuous currents, close to 300, maybe 350 amps.
And that massive current is the Achilles heel of the 48V system. So where does the safety risk shift to?
It shifts entirely from electrical shock risk to catastrophic thermal risk. In our ACRI-Q, SYS Era 1 must demand a complete reprioritization of thermal management for these low-voltage lines. When you have 350 amps flowing, even a tiny increase in resistance, a loose connector, a bit of corrosion, it creates exponential heat, I-squared our losses. That heat builds up so fast and leads directly to an electrical fire.
So we save money on HV shielding, but we have to spend a lot on high amp connectors, thick bus bars, and a lot of monitoring.
Exactly. Your BMS has to have incredibly precise contact impedance monitoring. You need dedicated thermal sensors all over your high current paths. You need specialized 48V contactors that can actually handle quenching the huge arcs you get when you shut down those currents. The simplicity of 48V is, it's balanced by the need for absolutely impeccable current path engineering.
Okay, let's pivot to strategic path B high voltage, say 96V up to 350V. This is the choice for the Wuling, the Toyota, the more performance-oriented L7s. What do we gain, and what mandatory costs do we immediately take on?
You gain performance, the ability to hit 80 kilometers and hold there. You get better regenerative braking, and crucially, you can support fast charging. Plus, lower current means smaller, lighter wires, which helps with mass. But the moment you cross that 60V threshold, you inherit two very complex mandatory ASIL-CD systems.
System 1, REQ-SYS-03, the High Voltage Interlock Loop, HVIL. Lay out the non-negotiable complexity here.
The HVIL is a continuous low-voltage hardware circuit. It physically snakes through every single high-voltage component, the battery, the VCU, the onboard charger, the PDU. Its whole job is to check for physical integrity. If that loop is broken, a service panel is open, a connector vibrates loose.
Or a minor crash.
Or a minor crash, exactly. If that loop breaks, the system has to react instantly.
And how fast is instantly?
The SOR must mandate that if the HVIL loop breaks, the main contactor has to cut the high voltage power in under 100 milliseconds. And on top of that, the bus voltage has to be discharged to below 60 volts within 5 seconds. That requires a dedicated active discharge circuit. It's complex, it adds cost, but it's the life insurance against electric shock.
Okay, and the second mandatory system, REQ-SYS-04, the Insulation Monitoring Device, or IMD, what's its job?
The IMD is the guardian against slow, subtle degradation. It's constantly measuring the resistance between your high-voltage lines and the vehicle chassis. Over time, or with water getting in, that insulation can break down, creating a path to ground that can lead to a short circuit, a fire, or a touch hazard for anyone who touches the car.
And what are the specific thresholds we have to write into our SOR for the IMD?
Two critical thresholds. First, an alarm has to be triggered if resistance drops below 500 ohms per volt of system voltage. That's a warning. Get service.
Right.
But critically, the system must physically cut the high voltage if that resistance drops below 100 ohms per volt. That level of precision and rapid response requires specialized IMD hardware that the 48V system just completely avoids.
So the strategic takeaway is crystal clear. 48V minimizes shock risk, but it maximizes thermal complexity and caps your performance. High voltage gives you the performance, but it forces you into expensive, high-integrity systems like HVIL and IMD.
Precisely. And our SOR has to lock this choice in on day one. If we're targeting 80 kilometers, the HV path is almost certainly necessary. And that means we have to budget for all that ASLD complexity right from the start.
Okay, we've set the regulatory landscape, we've made the big architectural decision, now we get into the real core process of functional safety. The hazard analysis and risk assessment, the HARA. This is what sets our ASIL requirements.
Right. And for LSEVs, you can't just copy and paste the HRA from a big M1 passenger car. It's a different world. You have to account for the unique operating design domain, the ODD. That means constant interaction with pedestrians, cyclists, what we call vulnerable road users or VRUs.
Okay.
It means operating in congested cities, a higher risk of water getting in because the chassis is so low. All these unique factors.
Let's start with the most critical hazard, the one that always dictates the highest ASIL level. Case study 1, unintended acceleration. The pedal fails, the control unit fails, the vehicle just takes off.
So we apply the ASIL matrix. Severity, exposure, and controllability, S, E, and C. For severity, SS3, fatal. Even a light vehicle hitting a pedestrian at 80 kilometers an hour is absolutely catastrophic. There's no debate. For exposure, E, E4, high frequency. These vehicles live in cities. They're constantly starting and stopping near crosswalks, near people. The exposure to the risk is constant. And for controllability, C3, difficult to control. The electric motor response is instant. If you dump full torque, the light mass of the vehicle means it just launches. The driver has almost no time to react and hit the brake before an impact.
So S3, E4, C3, that combination leaves no room for argument on the ASIL level.
It mandates ASIL-D, or at the very, very least, an extremely robust ASIL-C with a mountain of justification. Our SOR is going to mandate ASIL-D for the entire torque request path. It is the non-negotiable cornerstone of the whole system.
Okay, now this is where the engineering art comes in, the part that lets us meet that dual constraint. We need to find areas where we can safely and legally tailor the ASIL down to save some money. So case study 2, unintended deceleration or loss of traction. What if the vehicle just suddenly loses power in traffic?
This is our critical cost-down opportunity.
Sure.
The failure here is the sudden loss of power, not the unintended application of it. So for severity, S1, maybe S2, minor to medium, you're at low city speeds, a sudden power loss means you just coast down. The result is usually a minor fender bender, not a catastrophe.
Okay.
For exposure, E. E4, again, it's high frequency. But for controllability, C1. Easy to control. The driver immediately knows what's happened, and because the vehicle is so light and slow, they can easily just glide it over to the side of the road.
So we've got S1 or S2, E4, and C1.
Yeah.
What does that give us?
It results in QM, quality management, or ASIL-A. And that distinction is pure gold for the engineering team. Our SR has to exploit this. Because we've rigorously justified that low risk, we can specify that components that only handle the loss of traction function can use cheaper, industrial-grade, quality-managed chips.
So, for example, a part of the VCU that just handles the power-on sequence. If that failed, you'd only lose power. We could use a cheaper chip there, which frees up budget for the ASIL-D torque path.
That is risk-based tailoring in a nutshell. You spend your safety budget where you have S3 fatal risk, and you justify cost savings everywhere else.
Okay, now for the exception to all tailoring the battery, case study 3, thermal runaway leading to fire explosion. This brings us right back to that GB 38031 2025 standard.
No debate here. The analysis fixed. Severity? S3. Fatal. A fire in a tiny LSEV cabin gives you seconds, if that, to escape. Exposure, E4, high frequency. The risk exists every single second the vehicle is on or charging for its entire lifespan. And controllability, C3, uncontrollable. Once thermal runaway starts, it's a chemical chain reaction. The driver can do nothing.
Which means a mandatory non-negotiable ASIL-D for all battery protection functions.
Correct. The systems that monitor and prevent overcharge, overdischarge, extreme temperatures, they all have to meet ASIL-D standards. We can't compromise on the integrity of the battery management system, the BMS, because the consequences are just too severe.
And just briefly, any other high-risk systems we need to consider?
Loss of brake assist has to be ASIL-C or D. Losing your ability to stop is obviously catastrophic. Something like self-steering, if we were to implement it, you could maybe argue for ASIL-B.
Why lower?
Because the steering torque on a little LSEV is low enough that a driver can usually physically overpower an erroneous steering command. That improves the controllability score a bit. But even ASIL-B is a huge undertaking.
So we've locked in ASIL-D for unintended acceleration. The challenge now is how do we actually achieve that without the super expensive multi-core lockstep MCUs you find in high-end cars? We need a cost-effective architecture.
We implement the gold standard for this problem. It's called the EGAS 3-layer monitoring concept. It's a strategy that evolved over decades to deal with exactly this failure mode. It uses multiple independent layers of checking, often with simpler components, to get the same safety level as one big, expensive chip.
Okay, let's break down those layers. Level 1. The functional layer.
Level 1 is the main brain. It's running the complex control algorithms, reading the pedals, calculating the precise torque you want, and driving the motor. It's all about performance and efficiency.
And then level 2, the functional monitoring layer. What's its job?
Level 2 is the first safety net. It usually runs in a separate simple processing core, or in a dedicated protected time slice on the main chip. Level 2 doesn't do the complex motor control. It does a parallel but much simpler calculation. Its only job is to figure out the maximum allowed torque based on simple inputs like pedal position and vehicle speed.
So level 1 is asking for the optimal torque, and level 2 is checking if that request is sane. How do we define that relationship in the SOR?
That's REQSYS-05. If the level 1 core requests a torque that is higher than the level 2 safe maximum, plus a little tolerance, level 2 must have the independent authority to kill the output. It's like an automated co-pilot. If the pilot L1 demands full throttle when the plane is at the gate, the co-pilot L2 says nope, not allowed, and shuts it down. It checks the logic of the request.
Okay, that brings us to level 3, the controller monitoring layer. If L1 and L2 are on the same piece of silicon, what happens if the chip itself just crashes or goes haywire?
That is the exact vulnerability that L3 protects against, a common cause hardware failure. L3 is an external independent failsafe, and it's mandated by REQ SYS ESO 6. It requires you to use an external watchdog or a dedicated system basic chip, SBC.
And it has to be external hardware.
It must be. If the main chip gets stuck in an infinite loop, any watchdog running on that same chip is also stuck. The external watchdog has a continuous question and answer dialogue with the main chip. If the main chip failed to answer correctly or on time, the external monitor just assumes it's gone rogue.
And what power does that external monitor have?
It has the independent hardware-level authority to trigger what we call the second shutdown path. It physically cuts the power going to the motor's gate driver. It completely isolates the motor from the failing VCU. This triple-layer approach is how you get to ASIL-D without a single, massively complex chip.
Let's talk about the inputs, the accelerator pedal. We need redundancy there. REQ SYS07 says dual path sensors, but you mentioned that just having 2 isn't enough to prevent a common mode failure.
Correct. This is a classic trap. Imagine both your sensors run off the same 5-volt power supply. If that power supply drifts a little high or gets some electrical noise, both sensors might read high at the same time. The system sees 2 consistent but incorrect high readings and still causes unintended acceleration.
So how does our SRR engineer around that?
We mandate inverse correlation. For example, sensor A reads 0 volts to 5 volts. Sensor B has to be designed to read 5 volts down to 0 volts. Now, if there's a power supply drift, one sensor reads a little high and the other reads a little low. The VCU is constantly checking that the sum of the 2 signals is always 5 volts. If that sum deviates, it knows there's an electrical fault and it shuts down the torque.
That's a clever fundamental safety trick. Okay, let's talk chips. What specific hardware should the SRR suggest for the VCU and BMS?
So REQ-HW ASIL-1 says the core controllers have to be ASIL-B certified or higher. For our L7E, I'd recommend the NXP S32K3 series. It's not the cheapest chip, but it's a winner on total cost of ownership because it has integrated lockstep cores. These cores run the L1 and L2 calculations simultaneously and compare the results right there in the hardware.
So the hardware does the heavy lifting, which simplifies the software.
Massively, it flattens the development time. For less critical roles or for a really low-cost L6E, we could recommend something like the Microchip AVR DA series. These are smaller, cheaper, ASIL-C-ready chips, perfect for simple monitoring functions rated at ASIL A or B.
And finally, that second shutdown path, REQ-HW OZR2.
This is the physical kill switch. It's the execution of level 3 monitoring. The motor controller must have an independent physical input, a wire that comes directly from that external watchdog that can physically disable the motor gate driver. It's the only way to guarantee that if the main VCU completely fails, the hardware can still force the motor to freewheel. It's the ultimate line of defense.
Let's dedicate this section to the battery. It's our other ASIL-D component, and it's subject to those ruthless demands of GB 303031-2025. This part of the SOR has to be completely non-negotiable.
It does. The standard is no fire, no explosion. So our strategy has to be multi-layered. We have to integrate passive physical defense with an active, intelligent BMS.
So REQ Batchy 01 physical protection, where do we start? With the chemistry itself.
Chemistry is your first line of defense. We have to strongly recommend lithium iron phosphate LFP cells. LFP is crucial for low-cost LSEVs because it's just inherently more stable. Its thermal runaway triggers at a much higher temperature than NMC cells, and the reaction is milder. It just gives you a bigger margin of error.
But LFP cells can still fail. Propagation is the enemy. How do we stop one bad cell from taking out the whole pack?
The requirement is thermal propagation prevention. This means you have to design a high-resistance thermal barrier between cells. The SRR must mandate the use of aerogel insulation, probably 2 to 3 millimeters thick, between cells. Aerogel is a fantastic heat blocker. It disrupts the heat transfer that would otherwise trigger the neighboring cells. And this has to be validated with thermal simulation before you build anything.
And what about the no explosion part of the standard? That's about managing internal pressure.
Exactly. That requires specialized pressure management and venting channels. When a cell goes, it ejects a huge volume of hot, volatile gas. If that gas is trapped, the battery case becomes a bomb. So you have to design dedicated, efficient venting channels to get that hot gas and ejecta out of the enclosure and away from the passenger cabin.
Okay, that's the physical defense. Now, the active side. The BMS active safety strategy, REQ BADT 0203. LFP has that famously flat voltage curve. How does that make the BMS's job harder?
It's a huge functional safety challenge. An LFP cell's voltage stays almost perfectly flat for about 80% of its charge. So a tiny measurement error, say 5 millivolts, which in an NMC cell might be a 2% SOC error, could be a 20% SOC error in an LFP cell on that flat plateau.
And that means you could be dangerously overcharging the cell without even knowing it.
Precisely. So REQBTO2 has to mandate extremely high precision voltage sensing, less than 2 millivolts of error. And we must use advanced current integration algorithms, specifically a Kalman filter. A simple algorithm just can't track the SOC accurately enough. A Kalman filter can. And that's essential for preventing the root cause of runaway, which is overcharge-induced lithium plating.
So it sounds like the ACell DBMS needs to be more than just reactive. It needs to be predictive.
That's the ultimate goal. REQ BADI CDR3, proactive detection. The SRR has to require the BMS to integrate internal short-circuit detection functions. These are algorithms that monitor very subtle, long-term trends like abnormal self-discharge rates or tiny inconsistencies in cell voltages that can show up hours or even days before a cell actually goes into thermal runaway.
And a final point, what if we enable fast charging on our LSEV? That's another high-risk area.
REQ BADI CU4 covers fast charge protection. Charging hard in the cold is a surefire way to cause lithium plating and damage the cells. So if you support fast charging, the BMS must use a temperature-based dynamic charge map. It has to use real-time temperature data to strictly limit the charging current, throttling the speed based on the actual thermal conditions no matter what the charger wants to supply. Safety has to override speed.
We've got the technical specs down, but our SR also has to define the organizational structure, the Functional Safety Management FSM. We know from experience that great tech fails if the culture is wrong.
ISO 26262, Part 2 is very clear on this. Process and management failures are a common root cause of critical safety incidents. For a new LSEV team, establishing structural independence is vital. You have to prevent safety from being compromised by schedule or budget pressure, the very definition of our dual constraint.
So how do you structure that independence?
REQ FSM01, independent oversight. The functional safety manager, the FSM, must be organizationally independent from the project manager, the PM. If the PM reports up a chain that prioritizes time to market, the FSM has to report laterally, directly to the CTO or the quality director. This gives the FSM the authority to hit the brakes on the project if safety is at risk, without fearing for their job.
And once the structure is there, we need the paper trail to prove it.
Yes. We mandate the creation and constant upkeep of the safety case, REQ FSM03. And this isn't a summary document, it's the entire exhaustive audible evidence trail. It covers everything from the initial HERA to the design to software unit tests, integration tests, all of it. For a new platform, this documented proof is the only way you'll satisfy certification bodies.
LSEVs rely so much on outside suppliers for chips, BMS software, motor controllers. How does the SR manage safety across that whole supply chain?
Through something called a Development Interface Agreement, or DIA. REQ FSM 04 and 05 require that a DIA is signed with every single safety-relevant supplier before any real work starts. This agreement clearly spells out who is responsible for what.
And what's that division of labor look like?
The OEMR team, we own the vehicle-level HRA and the high-level safety goals. But the supplier is responsible for the detailed implementation of their own component. But crucially, the OEM retains the right to independently review and approve the supplier's safety work, especially their FMETA reports. We need to see the raw data on component failure rates, not just a glossy summary.
Okay, design and management are in place. The final hurdle is proving it all works when things go wrong.
The ultimate verification step, it has to be mandatory fault injection testing, which is RQ Test 001 done on a hardware-in-the-loop or HIL test rig. This is the most critical activity for the entire verification team.
We have to intentionally break the system. What does that look like in practice for our LSEV?
We simulate every fault we identified in the HATE-RE. We'll short-circuit the CAN bus. We'll corrupt a memory address in the VCU to simulate a software glitch. We'll introduce high resistance on a pedal sensor line. The goal is to verify that under every single one of those failure conditions, the system reliably and quickly goes to its predefined safe state.
Which for torque control is?
Immediate, total cutoff of gate driver power. The motor must freewheel. And for the battery, it's opening the main contactor and isolating the pack in under 100 milliseconds.
Let's close the loop on the strategic justification for the management team. Total cost of ownership. How do we present spending more on an ACell-D chip as a net saving?
The argument is purely about money and time. A safety feature looks like an upfront cost, but it eliminates these exponential costs down the road in software and certification. Take that e-gas monitoring. Developing your own ASIL-D-compliant software for that on a standard MCU can easily eat up an extra 10 to 15,000 engineering hours.
And in dollars, that is.
A lot. If we use a lockstep MCU like that NXP S32K3, it might cost, say, $5 more than a standard chip. But that built-in hardware checking can cut your software validation time by 30, maybe 50%, saving 5,000 engineering hours at a typical rate of $150 an hour. That's a $750,000 saving. That $5 premium is nothing compared to the salary costs and the schedule risk you just eliminated.
And that leads to a final sourcing recommendation, the white box strategy.
Absolutely. For a new team, the learning curve on ISO 26262 is brutal. Our SOR has to encourage deep cooperation with the chip makers NXP, Microchip, and Infineon to use their safety-ready reference designs. This white box approach lets our LSEV team focus on the unique challenges of the vehicle, not on reinventing a safe operating system from scratch.
We have successfully synthesized a huge amount of technical, organizational, and financial requirements into a comprehensive SOR for functional safety. This deep dive really shows that safety isn't something you just bolt on at the end. It has to be the first strategic decision you make.
That's right. And the core of this engineering art form is balancing that dual constraint. The central decision is that 48V versus high voltage split. That choice dictates whether your biggest headache is thermal risk from massive currents or the complexity of insulation monitoring and HVIL.
And no matter which path you choose, the implementation strategy is all about that decomposable, cost-effective integrity.
It is. It's the proven eGas 3-layer monitoring for the ASIL-D torque path, and it's the mandatory GB 38030 2025 containment strategy for the battery, which requires that meticulous physical design with aerogel and venting.
So for the chief systems engineer listening to this right now who's about to start this project, what are the 3 immediate, non-negotiable first steps from our SOR?
First, architectural freezing. You have to decide, 48V or HV, and lock in your key component suppliers for that platform now. Second, team and process foundation. Start the ISO 26262 training immediately. Formally establish that FSM role with independent reporting authority. And third, supply chain safety. Lock down your core suppliers for the VCU and BMS and make sure every single one signs the Development Interface Agreement, the DIA, which clarifies all the safety responsibilities.
And that brings us to our final provocative thought. We've shown how to achieve zero compromise safety while fighting these extreme cost constraints.
The most successful micro LSEV that achieves global dominance. It won't be the one that was cheapest on day one or the one that was fastest. It would be the one whose engineering team mastered the strategic allocation of their resources. They use tricks like the ASIL, a tailoring for loss of traction, and proactive detection in the BMS to achieve the same safety standard as a premium sedan. It proves that functional safety isn't a cost center. It's the most critical element of a cost-saving, globally competitive strategy.
A perfect way to frame it. Safety as competitive strategy. Thank you for walking us through this incredibly detailed and high-stakes engineering challenge.
My pleasure.
And thank you for joining us for this deep dive. We'll see you next time.